Hi kiddies, welcome to video 1.1 on measurement and data. So we kind of probably already have an idea of what measurements are and what data is. So we're going to get a little more specific about what we're looking for in science measurements. And then what do we do with those measurements in terms of the mathematics to make them consistent from one measurement to the other. So measurement and data. So what does it mean to be a measurement? So a measurement is a set of numbers and accompanying units that quantify an aspect of a physical object or its behavior. So it has numbers and units. I'm sure you've had teachers before say, hey, you need to show your units. Am I one of those teachers? Yes, of course, because I'm a science teacher. To say that I am 75 doesn't tell you anything, right? I could say I'm 75 kilograms of mass, and all of a sudden you know what the heck I'm talking about. So it's got to have the numbers and it has the units. It consists of all numbers that can be directly measured plus an estimate. So if I tell you I weigh 232 pounds, that doesn't necessarily mean I'm exactly 232. I could be 231.9, but my scale has maybe rounded that last digit up. So the last digit is always an estimate. We will kind of talk more about that in a minute. The numbers that can be reported are dictated by the apparatus used for the measurement. So if I am working in like a kitchen and I'm trying to get out the mass of maybe carrots for the recipe, it's probably going to be a different apparatus than they would use, let's say, in NASA labs where they're trying to figure out the exact mass of something that becomes really important in, maybe some calculation. Apparatus is going to dictate how exact of a measurement we can come up with. Okay? So when we're done with this measurement, we have something called significant figures. That kind of means to me that it's everything we're sure of plus an estimate. Everything is significant. Hey, that's 12.3 meters. I know it's 12. The 0.3 is the estimate. Or if I say it's 132.65 grams, that last 5 is an estimate. So everything we're sure of plus an estimate becomes a significant figures. So let's take a look at some examples here. Let's say I have this scale and I'm measuring this piece of tape, and it looks like the scale points to right about there. So what would we call this particular measurement? Well, it's 3 point something. We're absolutely sure that it's 3 point something, right? 3 point what? 6? Looks like 3.6 to me. I'll say it's centimeters. I don't really know what that unit was, but I'm not sure about this 6. So everything I'm sure of, I'm absolutely sure it's 3 point something. 3 point what? 6. So I have that estimate. Let's take a look at another example. Different type of scale here. Let's say that these maybe are centimeters, and it's really a close view. So there's 1 centimeter, there's 2 centimeters. I know this is 1 point something. Would you agree? It's past 1, it's not yet 2. So it's 1 point what? Well, here's 1.5, here's 1.6, here's 1.7. It's past 1.7, but not to 1.8. So I'm absolutely sure that it's 1.7 something. Now the next digit. It's 1.7 what? I don't know. Maybe it's 1.77. That looks close to me. So is that the correct measurement? Suppose you saw it as 1.78. Would that be okay? Sure, because I'm not sure about this 7 here. That 7 is an estimate. 1.76? That's probably good too. So you can see that there's an implied error in this measurement. I'm sure about the 1.7 here. I'm guessing at that final 7. Another example. 0, 1, 2, 2 point something. 2 point what? I'm going to make a guess and say 2.8. Now, is that absolutely 2.8? Looks close enough to me. I know it's 2 point something, and 8 is my estimate. So that would be, we'll say the units are meters, 2.8 meters. Could it be 2.7? I could see maybe that being true. 2.9, probably not, but you get the idea on that particular example. Ooh. All right, so over here we have 0. And this side we have 10. Where's this line? Oh. 6? I'll pretend that's meters. I don't know. I can't really tell anything beyond that. I can't say it's 6 point something because I'm not even sure about the 6. So there is an example. 6 meters. Let's take a look at another one. Ooh, real life example. Okay, this is tricky. This is centimeters. Here's 11. Here's 12. Here's 13. This line right here is definitely past 12. So I know this is 12 point something. 12 point what? Well, it looks to be 12 past 12.1. So 12.1 what? 12.14? See, it's getting a little trickier now, isn't it? 12.14 centimeters. Now, am I sure about the 12? Yes, I'm absolutely sure about the 12. Am I sure about the 1? Yes, I can see it's definitely past that little 1 line, and it's not quite to the 2. Am I sure about the 4? No, that might not be true. So 12.14 seems like a pretty guess for this guy. Ooh, another one. Okay, there's my 6 centimeters. There's 7. So I know this is 6 point something. 6 point, well, there's 4, and there's 5. So it's 6.4 something. I don't know. Looks to be just a little bit past that 4. I'll call it 6.41 centimeters. I could have made a case for calling it 6.40 centimeters too, I suppose. Would that have been okay? Sure. 6.40, 6.41. But the important thing is that I have this decimal out there that's telling me, hey, I'm dealing with an estimate at the hundredths place. All right, this is a tricky one. Now, this guy appears to be right on that 2, as far as I can see. Just about on that 2. So, what am I going to call this? 2? Well, that would imply that the 2 itself is the estimate. If, for the sake of the argument, the line were up here, what would you call it then? And you're probably saying to yourself, I don't know, 2.1, 2.2? That would be correct. But it's not there. It's actually on the 2. So if it were 2.2 up here, but now it's down to the line, this would actually be called 2.0. How is that different than 2? If you tell me 2, then I'm thinking, it's somewhere around 2. It could be close to 3. It could be down by 1. It's somewhere around 2. If you tell me 2.0, now I know that it's really just in this little area right here. So really close to that 2.0. Maybe it's close to 2.1. Maybe it's down towards 1.9. But it's close enough to that 2 where I'm calling it 2.0. That's kind of interesting. So, do 2 meters and 2.0 meters indicate the same thing? Again, so if I'm looking at a number line, all right, let's say I was looking at a scale that started at 0 and went to a 5 here. And that the line I was trying to measure went about that far. To me, that looks like 2. Okay? That's about a 2. Now, if I had a different scale and it were measured 0 here, 1 here, 2 here, 3 here, 4 there, and the line went to here, now I'd call that 2.0. So do you see the difference between 2 and 2.0? So when you say 2 to me, it's somewhere in this region. Somewhere around there is 2 to me. Now, if you say 2.0, I'm saying, oh, it's somewhere in this region to me. So the 2 has a much broader error than 2.0, which is smaller. And obviously, if this scale can pull it off, then we can get to 2.00 if it were actually graduated in between here to allow us to actually identify that. That scale wasn't, but it would be possible. All right, so back to this guy. Do 2 meters and 2.0 meters indicate the same thing? Not really. No, one has a much smaller range of error than the other one. All right, so once we've done this, I tell you, all right, I am 132 pounds. And so you know I'm 130 something. It might be around 2, might be 120 or 233. It might be 231, but I say 232. You get the idea what I'm talking about. That would be different than me saying I'm 232.657 pounds. Because now all of a sudden, you know I've measured the 6, the 5, and the 7's the estimate. So when I report data, we come up with this thing called significant figures. And we always abbreviate that as Sig Figs. Significant figures. So what are significant figures? Just a few rules. All non-zero numbers are significant. Zeros between non-zero numbers are significant. Zeros to the right of the last non-zero number are significant if a decimal point is present. And zeros to the left of the first non-zero number are not significant. So you guys could pause this for a second, write this down. This is going to be important for you to know. So let's take a look at this data right here. What are the significant figures? How many of these numbers that I'm looking at here are significant? So 12.3 grams. First rule says all non-zero numbers are significant. So this represents 3 Sig Figs. There are 3 significant figures. They're all significant. All right, how about 13.908 milliliters? All non-zero numbers are significant. Zeros between non-zeros are significant. So this represents 5 significant figures. 12.20 Celsius. So we learned that the zero actually does matter. 12.2 and 12.20 mean different things. Zeros to the right of the last non-zero number, meaning this guy, are always significant. 12.2, 12.20, hey, that 0 is significant. This is actually 4 Sig Figs. All right, 0.0012 Kelvin. The last rule says zeros to the left of the first non-zero number are never significant. Because if you think about it, there is a 0 out here as well. There's a 0 out here as well. There's a 0 out here as well. There's an infinite number of zeros going on out there. We just don't report them. Why? Because they're just placeholders. So are these zeros. The decimal does not really affect that. There are only 2 Sig Figs in that measurement, the 1 and the 2. Zeros to the left are not significant. All right, 13.03 milliliters. That is 4 significant figures. So all the numbers there are significant. All right, 4730. So kind of work your way from left to right until you hit something that's not a 0. Then you start counting. So I've got 1, 2, 3, 4 significant figures here. The 0 to the right is significant. There are 4 Sig Figs in there. So we're going to do the same thing here. We're just going to work our way left to right until we hit something that's not a 0. Then we're going to start counting. So I have 1, 2, 3, 4, 5 Sig Figs. They are significant when they're to the right of the decimal. So, I'm sorry, to the right of the last non-zero. So there are 5 Sig Figs in that measurement. This next one, let's see, 1.00 kilograms. Zeros to the right are significant. This is 3 Sig Figs. All right, wait a second. Nothing significant, nothing significant. Start counting. 1, 2, 3, 4, 5, 6 Sig Figs in that guy. So all of these ones here are the significant figures. The zeros to the left of the first non-zero number are not significant. All right. So the other rule in the third rule says zeros to the right of the last non-zero number are significant as long as a decimal point is present. So that kind of affected like this measurement here or this measurement here. There's a decimal point present. If no decimal point is present, then the zeros are not significant. It's serving as an estimate. Like if I say, give me 12,000 grams of this substance, I'm not looking for exactly 12,000 grams. It's like saying 12,000 people were at the football game. No, that doesn't mean that, like one guy left to go get a soda or something like that, attendance drops to 11,999 people. It's like an estimate number. This actually represents 2 sig figs. If there were a decimal point here, then it would all of a sudden become 5 sig figs. But there's not, so we're not going to call it that. That's 2 sig figs. So now we know how to count our sig figs. Now, Houston, we have a problem. Let's take a look at this. Density, as you probably know, is just simply the mass divided by the volume, the amount of space it takes up. So if a student measures the mass of an object to be 12.3 grams, and then the volume to be 2.34 cubic centimeters, she would arrive at a density of, 12.3 divided by 2.34 comes up with 5.25641025641 grams per cubic centimeter. Do you see a problem with that? So what we learned earlier is that measurements are things we're sure of plus one estimate. So when I go back and I look at this work, this person was actually estimating way out here at this 3. All right? Over here, they were estimating at this 4. So one was estimated in the 100th spot, one was estimated in the 10th spot. Out here, we're in the tenths of trillionths of spots. So how could we know something so exact when the measurements we used to derive it, we didn't know all that well? So do you see the problem with that? We cannot report all this data because that data is just mathematical babble. It's junk. It really doesn't fit our significant figure rules. So we're going to have a couple things to write down now to understand how we deal with this problem. When we are adding or subtracting significant figures, the answer may contain only as many decimal places as the measurement with the fewest number of decimal places. Then we're going to round insignificant data as needed. Might want to pause and go ahead and write this down as well. All right, let's take a look at this problem really quick. 31.631 grams, we're going to add 2.23 grams. Now, we know from our previous discussion that this 1 is actually an estimate. So just to keep track of it, I'm going to write a little e above it so we know it's an estimate. In this other measurement, we weren't even sure about this 3 here. That was the estimate, right? Now, the question comes up, what number, when I add these together, is actually sitting in that spot right there? Now, you're thinking to yourself, 0, but that's not true, okay? We don't know what it is. We had to estimate this 3. So we're not really sure about this 3. Therefore, we have absolutely no idea what's out in this spot. It wasn't measured. We had no ability to measure it. We didn't even have the ability to measure this 3 here. So we have no idea what it is. When I start doing the math then, I'm just going to keep track of these estimates for a second. An estimated 1 plus I don't know. What is the value of somewhere around 1 plus anything else? Well, obviously, we don't know what that is. Somewhere around 1 plus I don't know is I don't know. All right, this next one. What is 3 plus an estimated 3? So 3 plus somewhere around 3, that would be somewhere around 6, right? That's a little estimate right there. Write a little e there. You wouldn't do this in a real calculation, but just to show you what it is, I'm going to write a little e there. 6 plus 2, those are both real numbers. So 6 plus 2 is 8. Decimal point, 3 and 3, right? So the answer I arrive at is 33.86 grams. That 6 is an estimate, so that's the last thing I report. Everything I'm sure of, plus this guy, that's the estimate. Of course, I got rid of that other stuff because I have no idea what it was. This number now fits our definition of sig figs. It's everything we're sure of plus one estimate. You'll notice from our previous rule, the number of decimal places in each measurement has to be figured out. Sorry. Remember our rule that when adding or subtracting sig figs, the answer can contain only as many decimal places as the measurement with the fewest number of decimal places. There are 3 decimal places here, there are 2 here, so really I can only report 2. Hey, that makes sense, doesn't it? So let's take a look at a couple examples here. What you need to do is actually just pull out your calculator and go ahead and practice these, okay? So what I know before I actually do the work here is that because this is addition, this is addition, this is addition, subtraction, subtraction, I'm going to be using this set of rules. The answer can contain only as many decimal places as the measurement with the fewest number of decimal places. So what do I know about this? It has 2 decimal places. This one has 3. So my answer can only contain 2 decimal places. So what you want to do is do it on your calculator, then round so it's only showing 2 decimal places. Okay? The next problem. This guy has 3 decimal places. This one only has 2. So our answer can only contain 2 decimal places. This one has 1 decimal place. This has 2. So my answer can only contain 1 decimal place. This has 3. This has 1. Answer is only going to contain 1 decimal place. Here's 2. Here's 4. The answer is going to contain 2 decimal places. So again, just plug them in on your calculator. So what you guys need to do now is actually practice these, round to the correct number of decimal places, and then check your work. So right now what I need you to do is just pause for a second, run these calculations, and then when you come back, start the video again, and you can check your answers. Go ahead and do that. Okay, so again, 2 decimal places, 3 decimal places. Our answer has 2. 3 decimals here, 2 here. My answer has 2. 1 decimal, 2 decimals. Answer has 1. 3 decimals, 1 decimal. Answer has 1. 2 decimals, 4 decimals. Answer has 2. Make sense? I hope so. All right, next rule. Rules for multiplying and dividing sig figs. A little bit different. They look the same, but there's one significant difference. When multiplying or dividing significant figures, the answer may contain as many sig figs as the measurement with the fewest number of sig figs, and then we round the insignificant data as needed. So this looks a lot like our addition and subtraction rules, but now we're looking at sig figs rather than decimal places. So when we're adding and subtracting, we're thinking decimal places. In multiplying and dividing, we're counting the sig figs. Our answer is only going to have as many sig figs as the measurement with the fewest number. So let's take a look at some examples here. This particular 12.3 divided by 22.3, this measurement has 3 sig figs. This answer has 3 sig figs. So my answer is going to have 3 sig figs here. Okay? Over here, this is 4 sig figs. This is 3 sig figs. So my answer is only going to contain 3 sig figs. In this example, that guy has 4 sig figs. You see why we learned to count sig figs earlier? That's 0 significant. There's 4 here. There are 5 sig figs here. So my answer must contain 4 sig figs. In this example, this is only 2. This is 5. So my answer can only contain 2. Here's 4 sig figs. Here's 5 sig figs. My answer can only contain 4. So again, same idea. You're going to put 12.3 divided by 22.3 equals on your calculator. In this particular example, it has to contain 3 sig figs. So you're going to round the data to show only 3 sig figs. So go ahead and take a minute, try these 5 calculations, scribble down your answer, and then come back and check your work. So go ahead and do that now. All right, so This one, everything looks pretty good here. It's like 3 sig figs, 3 sig figs, 4 sig figs, 2 sig figs. This one is 4 sig figs and 5 sig figs. Remember that if a decimal isn't shown, then the 0 to the right is not significant. So we can get away with this. This will actually work. If we had a decimal point there, that wouldn't be okay. But this is technically 4 sig figs. There is another way around that to help us get out of that problem, though. And that's about it for video 1.1. We've learned about measurements, everything we're sure of plus the estimate. We've learned to count sig figs. We've learned to use the sig figs in mathematical functions, adding, subtracting, multiplying, dividing. And that is it for this unit. We will see one another for practice, and I will see you in the next video. Thanks for stopping by.